Neuroendocrinology is playing a growing role in our understanding of mental disorders, and the hypothalamus, unfortunately, has been much ignored in neuropsychiatry, despite the fact that it controls many of the functions that are affected in psychiatric disorders. The book has the diagram of the various uh, hypothalamic nucleus. This figure here gives us a little bit more of a 3D picture. I'm not going to ask you to memorize each of the individual nuclei and their various actions, although this is a frequent topic on the neurology section of the psych boards, as well as in some cases increasingly in the neuroscience portion of the psychiatry exam. We're going to be focusing on the paraventricular nucleus, the lateral hypothalamic area, and the preoptic area. And here's just another view of it all. Each of these is a very nice, convenient summary of which nuclei in the hypothalamus influences which function. You'll see that there's an overlap of functions, and this area is very tightly packed, such that damage in one area will easily cause dysfunction in another area. And finally, this gives you another kind of more detailed view. Again, this is not to memorize, but for your reference in the future. Also not poorly understood is understood but not emphasized in neuropsychiatry is the inputs to the hypothalamus, which we see here. And you'll notice that one of its chief inputs is from the amygdala, and perhaps that's not surprising. Please note here that the colors represent different pathways. Red and green is not excitatory and inhibitory. We see that the mammillary bodies are sometimes regarded as part of the hypothalamus. They get there, as we've discussed already, that's part of the Pepez circuit. And the septal area will have direct input into the hypothalamus. Also, equally, perhaps even more important, are the inputs from the cortical areas. We get input from our prefrontal cortex and from the anterior cingulate gyrus, an area that we're going to be looking at in much more detail later on. The hypothalamic nuclei in many ways are final output action nuclei for a variety of behaviors, particularly the fight or flight response, sexual response. So it makes sense that our cortical areas are going to have some degree of influence over that. Now, when it comes to the efferents or the output, a large output is obviously to the brainstem, where the parasympathetic and the parasympathetic and then ultimately the sympathetic nervous systems are activated. We have an output back to the hippocampus through the Pepez circuit. So that tells us again that the Pepez circuit, particularly the fornix, is a two-way street. And the hypothalamus is informing what the prefrontal cortex, what it's up to. So we have this interesting bilateral, bilateral direction, bidirectional aspect of input from the cortex to the hypothalamus and from the hypothalamus to the cortex. And then finally, the anterior thalamic nuclei are part of these thalamocortical fibers that we touched on briefly in the first lecture, but we'll come back to when we're looking at motor function in detail. Now, it gets very complicated to try to sort out what the different hormones do. Ultimately, the great bulk of the hypothalamus, it exerts its influence through the anterior and posterior pituitary. We're going to be looking at vasopressin and oxytocin in the posterior. That's probably the easiest one to keep straight. But the interactions of dopamine, thyroid releasing hormone, corticotropin releasing hormone, growth hormone releasing hormone, and somatostatin, there's a really, as you can see here, a lot of interactions at this level before we get to the output here. And over here, we're looking at the interaction of growth hormone and somatostatin, ultimately producing insulin growth factor 1, which has a lot of neuropsychiatric or neurotropic properties. Again, not for memorization, but to appreciate the larger picture. All right. And just to make it more complicated, here are the many roles of somatostatin. We don't have time to go into it in detail in this lecture, but people are very interested in the multiple of effects that somatostatin has around, particularly around appetite regulation and growth, which we'll get to in a moment. All right, and here we are with appetite. First, some important concepts that are easily misunderstood, even by physicians. On the left, you see three concepts. The basal metabolic rate, that refers only to the minimum amount of energy that your body uses for its basic function while you're at rest. So imagine laying in your bed all day or laying on the couch all day, not sleeping, but just awake. Your body is going to use between 1,400 and 1,800 kilocalories a day. And that's generally going to be higher in men. Now that's contrasted with the daily energy expenditure, the DEE, which is the total calories your body burns in a day, and that obviously also involves activity levels. Now neither of these are confused with the FDA daily calorie recommendation, which is about 2,000 calories a day. That's something completely different from the other two variables, even though the numbers are similar. Now, also note that the lay word calorie is really 1,000 kilocalories. And I'll try to use kilocalories going forward because it's more accurate. Now, we've always assumed that this is the relationship between energy expenditure and physical activity. So our basal metabolic rate is constant, but then as we become more active, it's always been assumed that this is just a straight line that goes up forever. The more active you are, the more energy you use in a day. Actually, quite surprising, we tap out at about 3,000 kilocalories a day. Even if you're a marathon runner. Now, say that doesn't make any sense, and it's really difficult to wrap your mind around. And in fact, this gets to the danger of overtraining in people who are supreme athletes. That actually the body will start to decrease its metabolic rate and other functions, particularly reproduction in the immune system, in order to conserve the calories for the more vigorous activity. Now down here, I realize you can't see these very well, but what you also see is this is on the left, the daily energy expenditure for men, and on the right is for women. Women obviously have a slightly lower. It averages around 3,000 kilocalories per day, but look at the variability among individuals, and there's more variability for men. Now, over here in this left box, we found out that it's eating and weight is not like gasoline in an automobile. So back in 1965, they brought both overweight and lean adults into a lab where they ate nothing but tasteless gruel for several weeks. It was liquid dispensed from a container. And there were no other food cues around, and they measured how much people drank. The lean adults took in about 2,000 calories a day, what they were eating beforehand. They were surprised that the overweight adults only drank about 200 to 500 calories, and they lost weight, and more strangely, they never complained of hunger. I want you to kind of think about that for a little bit. As you know from yourself or from any patients you've tried to help with weight loss, that hunger is a major problem. People just feel driven to eat and they can't lose weight. Well, in a very controlled environment with no food cues, people would only eat 500 calories a day and not complain of hunger. And this study kind of led the idea, well, you could do stomach stapling, and grossly and morbidly obese adults can then ultimately live on only 500 calories a day. So it's very interesting. Now, the other set of interesting studies came from these people, the Hadza of Tanzania, Africa. They are one of the last hunter-gatherer peoples left in the world. And when they look at their eating, they eat a lot of meat. They eat the dik, which is this cute little animal here, which they think is no different than when we eat lamb or cows. So, don't be too animal lover about it. But they also hunt the kudu. Now, as you might imagine, that kudu is a lot harder to catch than or hunt than the dik, and this requires men working together, chasing the kudu through the across the savannah. In fact, the Hadza men spend more time talking about catching the kudu than they actually hunt it. But the point being, they have a heavy meat diet. They also like to eat honey from bees' nests, and the women will go out and dig tubers high in sugar. So contrary to the idea that early man was, paleo man was a vegetarian, was a plant eater, this is not the case. Assuming these people lived very much the way our hunter-gatherer forebears did, they were eating a high meat, high sugar diet. Why? But the Hadza have virtually no obesity, very low fat levels, and virtually no cardiovascular disease. And that's because the number of calories that they eat every day is quite small relative to Western society. And they exert a tremendous amount of physical activity in order to obtain this food. All right, so there are many unresolved mysteries of weight. We could do a whole lecture on this, actually. The heritability studies from twins that we talked about in the prior lecture is only about 40 to 70%. And you say, boy, that's pretty variable, and that suggests that we're looking at populations that are too heterogeneous. Obesity is polygenic, but the genes for obesity are pleiotropic, and they can be related to other psychiatric disorders. There's thousands of SNPs associated with variants, no SNVs, interestingly. Now, here's another interesting fact, which you probably experienced in your own life. You can't go on the treadmill and burn 500 kilocalories via exercise and then go out and eat 500 kilocalories of food and expect to not gain weight. It's just a sad fact. And in fact, if you only exercise and you don't reduce your caloric intake, you'll find it nearly impossible to lose weight. Because, as it turns out, our metabolism adjusts to maintain our weight. Now, importantly, exercise is good for your cardiovascular weight, even if you don't lose weight. This is hard to convey to patients who often say, well, I exercise and I don't lose weight, so why bother? Some people gain weight when they exercise. This appears is because of a psychological phenomena. People do 200 kilocalories of exercise at the gym and then say, well, now I'm going to reward myself since I worked out. I'm going to go get an ice cream cone that's 400 kilocalories, and thus they gain weight. But all said, brains do not have a simple set point at weight. There's nowhere in the brain where you have a thermostat that says I'm going to be 180 pounds. But there are mechanisms, complex mechanisms in the brain, which we'll look at in a moment, that sort of drive you to maintain your weight, whatever it is. All right. Obviously, our modern food environment is a major factor. These figures say it all. Put people in a laboratory and randomize them to either eat ultra-processed foods or unprocessed foods. People eat more of the processed foods, and interestingly, they gain more weight on the processed food, even if you adjust for the calories. So obviously they're eating more calories, but also calories from ultra-processed food may increase, may be more efficient at making us gain weight. And, when I was a child in the 50s and early 60s, going to McDonald's was a special treat that we maybe did a couple times a year, and we ate tiny little hamburgers that maybe had, a quarter of a pound, no, less than a quarter of a pound, You know, sometimes the little tiny McDonald's burgers that you see on the bottom of the menu. Nowadays, of course, people get the Big Mac and the and the quarter pounder or 2 quarter pounders when they go, and it's just so tasty they have to keep eating it. Now, the regulation of appetite is incredibly complex, involving multiple brain regions and hormones. So on the left, we have the orexigenic hormones. I tend to OX like ox, eat like an ox, can tell you that, help you remember it's appetite inducing. This includes ghrelin, the sort of grrr, you're hungry. It's produced when the stomach's empty. Peptide double Y, not to be confused with neuropeptide Y, orexin itself. And then on over the right, you see a long list of orexigenic factors. Now, you'll see on the diagram there with the hypothalamus, you'll see the lateral hypothalamic area on the left upper quadrant and the paraventricular nucleus on the right lower quadrant. Think of your LHA as kind of an ambivalent nucleus. Eat or don't eat, but a bias toward eating. Whereas the PVN is your on-off switch, or actually is your off switch. The PVN is do not eat, stop eating. All right. So the next thing we're going to look at is the location of the GLP-1 receptors. Now, these are in the gut. They are in the nucleus tractus solitarius. I'll talk about that in a moment. They are also on the ventral tegmental area and the nucleus accumbens in your reward system. And they're at various places in the hypothalamic nuclei. So GLP-1 receptors, quite a few different places, probably play a role in more than just appetite. Again, LHA, eat or don't eat. PVN, don't eat. Now, let's go down to the bottom. Let's go down to the gut. The vagal nerves talk to the nucleus tractus solitarius in both directions. This is part of the gut-brain axis. So once whether there's food in the stomach or there's not food in the stomach, the NTS knows about it, but also the NTS gets information from the liver and the pancreas. Now, what happens here is that when ghrelin is around, it's an oxygenic stimulus. It's going to inhibit calcium here. But when CCK or GLP-1 are around, or mechanical stimulus, your stomach and your small intestine are getting physically full, then we get activation of these calcium waves that activate neurons in the nucleus tractus solitarius. So the initial action of GPL1 agonism is at the level of the gut. But there's more. So here we have an overview of the central regulation of appetite. And I want to emphasize here that this is at 2 levels. The hypothalamic level involves the lateral hypothalamic area and the PVN, eat or maybe don't eat or don't eat. The arc, which I'll talk about in a moment, the arcuate nucleus. And then at a higher level, we have VTA, nucleus accumbens, and the prefrontal cortex. Think of this area as your motivation level. So you're kind of hungry on your way to seminar. That's done at the level of the hypothalamus. It's detecting the empty stomach, and so on, low glucose sugar. At the motivation level, we're coming to lecture and we see the sign for DALA, as we mentioned early. That's the motivation level. The VTA is going to send information to the nucleus accumbens onto the prefrontal cortex. Now, again, in this diagram, the green color refers to those effects that increase appetite, the red color to effects that decrease appetite. This doesn't necessarily tell you the stimulatory action of the neurotransmitters itself, but I think it's a little easier to understand this way. So here we're eating, we got GLP receptors being activated, talking to the NTS. The NTS is shutting off the VTA. So let's say just before you came to lecture, you left the VA and somebody brought donuts and you ate 2 big juicy donuts. So hopefully GLP-1 is sending the message that, you know, we have no motivation to eat. All right. Now, on the other hand, so here gets things really get hairy. So here's the arcuate nucleus, and it is when NPY is around, it's going to switch off the PVN. I know that's a little confusing with the green, but you want to turn off the don't eat nucleus. Similarly, when the GLP-1 comes on, well, that's in red, it's going to turn on the PVN nucleus. Not eat. Hey, we're full, don't eat. And notice how it's turning off the VTA. So don't let the colors freak you out a little bit here. In contrast, in the LHA, we've got to kind of notice the LHA can go either way depending on the balance of things. For instance, the LHA here can be turn off the orexin, which stimulates appetite, or it can turn it back on via GABA. And it has this more complex interaction with the VTA. So on balance, as an organism, we're more prone to eat than not eat. We've got more eat than we do don't eat. But the critical point being that our brains are set up to look at the acute hunger and the amount of food that is present at any given time. Now let's talk about leptin. The triangles show you where the leptin receptors are in the brain. And leptin is produced by the white adipose tissue. All right? And when leptin levels decrease, i.e. we are losing weight, then a series of processes are NPY in the arcuate nucleus is triggered to increase hunger. The don't eat part of the LHA is decreased, and the eat actions of the LHA are increased, and motivation is increased. So you've decided you're going to lose weight. Your prefrontal cortex says, okay, my cholesterol was 220 at my last visit. You know, my girlfriend tells me, you know, she's tired of looking at my gut. I am gonna lose weight. So you go out and you exercise and you cut back. You don't go to Dallas. You stop by, I don't know, you get a salad somewhere, wherever you can get a salad around Eckerd, although it's not easy, I can tell you that. So you start losing some weight. Your white adipose tissue goes down. Well, your prefrontal cortex knows this is good for you in the long run, but our evolutionary mechanisms are saying, hey man, we're starving. We've hit the famine. Something's wrong. You go eat, man. Go eat. You know, we're losing weight here. And so this shows, this is basically the same diagram, but it's showing here again where the leptin is inhibiting the orexigenic pathways and activate. Again, red doesn't mean inhibit. Red means you activate the anorexic pathways to if leptin is high. So now leptin also works really more over the long term, but not particularly. That long term is a little questionable, and it doesn't, like I say, because you don't have a brain thermostat, it doesn't always do the greatest job for you, and it is more working against you to lose long-term weight. And also, the development of leptogenic drugs has not really gone very far. All right. So here's our main man now, our GLP-1 receptor agonists. It's pretty easy to say that if you stimulate those in the intestine, you're going to increase the satiety signals directly, but you're also increasing all of the anorexogenic pathways, and perhaps most importantly, you are decreasing the motivation to eat. And what many people are saying is that many patients say that the reason they couldn't lose weight is when they didn't eat, they were bothered by what's called food noise. That is the constant signals from the environment. I want to eat, I have to eat, and they would become dysphoric when they couldn't eat. And the GLP, with taking the GLP-1 agonist, all of a sudden that has gone away. Now, think back to the study I mentioned in the lab where they're drinking the gruel. That worked as well as a GLP-1 agonist because the external signals of reward were not there. But we can't live in a lab all our lives. We're constantly around where we're smelling food, we're seeing the signals of food, and that generates these orexigenic pathways. And of course, we could just change our society and have less processed food around and fewer fast food restaurants. Instead, we're going to use $10,000 plus drugs to do it for individuals, which raises an interesting question. What will happen to the restaurant industry if suddenly everybody were taking GLP-1 agonists and losing weight? Discuss amongst yourselves. Now here's orexin. I don't want to spend too much time on this because it's a little more of a secondary player, but it does have an extensive projections through the brain, so perhaps we don't appreciate it as much as we should. It has two types of receptors. In narcolepsy, people have reduced orexin neurons, and so using a receptor agonist makes sense. Now, it is appetite promoting, and it's also wakefulness approach. It stimulates wakefulness. Here's the mechanism over here. The bottom line, and that's why, of course, if insurance companies will permit us, we can use the orexin antagonists to help insomnia. All right, so let's shift gears to aggression, although we certainly do get aggressive when we can't eat. So mice, generally speaking, don't like each other, and particularly male mice, and they will work hard to try to get access to a mouse that they can fight with. And here's a little good example for you here.
Researchers are looking at aggression in other creatures as well. In male fruit flies, a similar network of neurons can provoke a fight over food or females. Whether you're a fly or a mouse, rage networks may be wired differently in males and females. But across the animal kingdom, sex and violence seem to be closely linked. In fact, some of the same nerve cells that drive mice to fight might also drive them to mate. Digging into the roots of aggression could also help explain and perhaps one day control violent behaviors in humans.
So what they're showing here in this is the looking at populations of ventral medial hypothalamus, actually the ventrolateral part of the ventral medial hypothalamus, and gain of function generally leads to a more aggressive mouse, whereas loss of function manipulations lead to reduction in aggression. And this just shows you the various inputs into the VMH, and such that the VMH neurons code the overall aggressive state, like how irritable the mouse is, how quickly it detects the aggressive stimuli, and how quickly it initiates the attack. So the minute the mouse sees the intruder, the VMH firing starts to increase, and if it continues to be active after the intruder removed, then the mouse, he's a bully, he's not done. He'll go after the next mouse. Now, interestingly, the premedial optic areas fire in response to females. And again, this is in rats. So it might be the two together, medial preoptic area and VMH working together, then transform it from aggressive behavior into normal sexual behavior. So there have been neurosurgical techniques to actually do deep brain stimulation in the hypothalamus, and that shows you kind of they get it right in the spot they need to get it. And these are mostly a series of small case studies in individuals with intellectual disability who exhibit really severe aggressive behavior and self-injury. I work at Mission Road Developmental Center with intellectually disabled adults, and I can tell you self-injurious behavior is a very difficult thing to treat and can be very tragic in terms of the long-term morbidity. And you can see that there have been improvements in these symptoms. Now, this area probably isn't researched as much as it should be. It's not, as you can see here, you can also induce pretty significant side effects. And research in this area is hampered by the unfortunate history of the lobotomy. Everybody's fine with DBS for Parkinson's disease or for obsessive compulsive disorder or even treatment-resistant depression, but people are very nervous about using it for suicidal behavior or maladaptive aggression. And that's a whole topic in and of itself. All right, now we're done with, let's look at oxytocin and bonding. So here's the medial preoptic area, which receives oxytocin. Oxytocin is obviously directly released from the posterior pituitary during childbirth and, of course, during breastfeeding. But it has a wide influence on other aspects of the limbic system, particularly the reward system. And you want to distinguish between oxytocin and vasopressin. You can see that they are mainly distinguished by this one amino acid here, and also here. They have similar but slightly different actions, as you can see here. I'm going to focus mostly on oxytocin because that's where the research has been. And it's not just the love hormone. It really has a lot of physiologic and psychological effects. And in humans, we can administer it in 3 different ways. The nasal spray is the most common, but its effects are very short-lived. And you really can't go around snorting oxytocin every 5 minutes to change behavior, and thus oxytocin really has not proven to be useful in any way as a psychiatric medication. But you see, you do tend, whether you give it, you get activation in limbic areas as you would expect. Now, in this study, people are given either oxytocin or placebo, and when they're on oxytocin, which are the dark bars, you can see that they, looking at random faces, they perceive them, they're more likely to recognize, feel like they know the person, and they're also more familiar. And people feel that oxytocin and vasopressin work together to look at a number of, or to influence a number of social behaviors. Notice that vasopressin may have a bit of a role in aggression. Now, again, you don't want to think of oxytocin as the love hormone. What it does appear to do, it does enhance pair bonding, as we'll see in a moment, but it also enhances in-group bonding, but it may also influence out-group aggression. So what they're doing is that people are doing a task here where there's intergroup conflict. And when people are on oxytocin versus placebo, they are more united to their in-group that they've been assigned to, and they're more aggressive or dismissive or rejecting of the out-group. Now, I've been looking for the reference for years. I've not been able to find it, but I'll keep trying. Apparently, a study was done some time ago with Yankees fans and Red Sox fans. And they showed them an infamous video of a World Series where a Red Sox fan bobbled an easy catch and allowed the Yankees to get on base, and the Yankees ultimately went on to win the series. And when they give oxytocin, Yankee fans were more euphoric, and Boston fans were more enraged when they viewed this particular clip. So again, oxytocin may enhance our pre-existing prejudices. Again, it's not just the love hormone; it can be the anger hormone as well. Now, this is a fascinating study that looks at pair bonding. So here, men were the subjects, and the females who were the experimenters. They were in the room, and the men thought the female was a fellow participant, but they were actually a confederate of the experimenter. And it's a triple-blind experiment because the people in there were unaware of the reason for the study. They thought they were getting a nasal spray that was a decongestant, when really they wanted to look at, obviously the true purpose was to study the effects of oxytocin on social behavior, in this case, social distance. So they have men who were either single or in a committed relationship. And the female confederate would move into the social space of the men. And they looked at what oxytocin did as a function of that. And quite simply, men who are in the committed relationship kept their distance from the female confederate. So if she moved her chair closer, they would slide back. And this was irrespective of eye contact or whether the female was coming from a long way away or was starting from a closer position. And so that really, again, tells us that oxytocin probably plays a role in pair bonding. So now let's talk about sex and parenting behaviors. Oops, I'm a little ahead of myself. Let me first talk about some neurophysiology here. Here is your basic sex hormones. That will be of no surprise to you. Do note that testosterone slowly declines in males, and there's debate about whether replacing testosterone at this age is a good thing. Testosterone does exist in females, and its role is poorly understood. Similarly, estradiol exists in males, and its role has been poorly studied. Here are the hormones related to menstruation and pregnancy. And of course, remember that prolactin peaks at childbirth and then is involved in producing the milk right after the breastfeeding, whereas the oxytocin creates the milk letdown reflex and obviously must surely play a role in mother-child bonding. Here's our male reproductive hormones. Remember that men have FSH and LH, and that are largely related to spermatogenesis and production of testosterone. Now, you've probably all heard about roid rage. There's a meta-analysis of studies looking at artificial androgenic steroid use And they do find an effect of these on aggression, although these effect sizes are very small. So the the and the effect was a lot more modest, and it wasn't dose related, which is kind of interesting. And once again shows us, even though testosterone has very direct and large effects on muscle growth, the psychological effects are much more subtle. And another important point that will be much studied and much debated in the years ahead, of course, the Y chromosome has the SRY gene, which creates the testes, and this is what converts the default female body and brain in the fetus into a male body, a penis and testicles, descended testicles. And maybe we get this burst of testosterone prenatally right after birth and then not again until puberty. What is happening in this critical period? We say we are masculinizing the brain, but what does that mean? How much of the behavioral differences between men and women are ultimately due to these biological effects versus societal effects? Again, and we could do a whole lecture or a whole course on that. Some accidents of nature give us some clues. Complete androgen insensitivity syndrome. These people are born XY, but they have a mutation in their testosterone receptor so that the fetus is born as a phenotypical female. They appear to have a vagina. They're generally raised as girls, and they adjust very well to the female role. They generally present at puberty because they do develop breasts. There's enough testosterone converted to estrogen to create breasts. But they come in for the workup for primary amenorrhea, and it becomes very obvious on the gynecological exam that they don't have any internal genitalia that are, or excuse me, any uterus or ovaries, and then genetic testing confirms it. Most of these individuals continue in their role as women. And as far as we can tell, pre-diagnosis gender identity issues are very rare. So that does, if you don't have this testosterone effect in the early brain, you do indeed adopt a female role. Now, even more interesting is so-called guevedosis, or penis at 12. This is a rare mutation that's common in a village in the Dominican Republic. These people have a partial deficiency of 5-alpha reductase, and so the children who are XY appear to have a vagina. They're raised as girls. Now, these individuals do have exposed to testosterone in the brain. And what's interesting is then when adolescence comes and testosterone levels are higher, it overcomes the deficiency, and these individuals suddenly develop, their testicles drop, they develop a penis, their voice changes, and they become boys. And this is actually a culturally accepted phenomena in this village. It doesn't cause any unusual degree of distress. And and many of these families kind of know that they might have a girl with this because these girls are quote unquote tomboys when they are younger. So that does not mean that having some masculine interests as a child in Western society is due to any kind of hormonal influence prenatally, because our expectations for girls have changed dramatically over the last several decades. Again, it's something we could have a whole course on. Now, I mentioned in earlier lectures the sexually dimorphic nuclei in the hypothalamus, and there has been some work to try to look at this in terms of sexual orientation and gender identity. And if we look normally in the preoptic area, males have a larger preoptic area nuclei, particularly younger, and it tends to shrink over time. And that actually occurs in both females. Their preoptic area nuclei shrink, interestingly enough. There's another set of hypothalamic nuclei, the interstitial nuclei of the anterior hypothalamus, not even on the diagram I gave you. But there's this tiny, tiny little area, INA3, where there are differences in men versus women or gay men versus straight men. And there's one guy in the world, D.F. Swab in the Netherlands, who has studied this both post-mortem studies and also in some neuroimaging studies. This is a very controversial area because these effect sizes are very small. You cannot look at the neuroimaging or post-mortem data and predict with certainty who is which sexual orientation or gender identity or people are. But it would make sense that if there's a physiologic cause of either homosexuality, same-sex behaviors, or gender identity issues, that would be the place that would be involved. All right, now let's look at the father's brain in childcare. So this study looked at 3 groups of people: primary care mothers, mother-child pairs, mother-baby pairs, father-child pairs where the father is the primary caregiver. And these were both gay men and straight men. And then finally a group of traditional fathers who were in a secondary role. And what this is showing you, the parent-infant synchrony. And you can see that there's no difference between the primary caretaker moms and dads in terms of how much they sync with with the baby. So anytime one watch very often in traditional families, watch the mom and the baby, and the mom's, oh, they're making eye contact, they're really in sync. Hand the baby over to the father, what the hell do I do with this? I'll hold them up in the air and shake them. So many fathers are not quite as synchronous, but when they take on the primary care role, that's quite different. And what they looked at in an imaging study is they were able to define the 2 networks, the emotional processing network, which is part of the default mode network that we're going to talk about in future the mentalizing network in purple, which we're going to talk about in later lectures. And they also found an emotional processing network involving the amygdala, the reward system, the VTA, and what you see here is that in the amygdala, the primary care moms and dads are very similar in their amygdala activation. The secondary father's not. But look here, you see in the superior temporal sulcus, the men are different, where they have more activation of that area relative to the moms, even if they are not the primary caregivers. So tells us the complexity of child care and neuroimaging.